So our second speaker for the afternoon is Professor Peter Corke. Peter is Professor of Robotic Vision at Queensland University of Technology, and he's Director of the Australian Research Council Centre for Excellence on Robotic Vision. His research is concerned with enabling robots to see and the applications of robots to mining, agriculture and environmental monitoring. He's a fellow of many illustrious societies and also editors and chief editors of a number of boards. He was a recipient of the Qantas, Rolls-Royce and Australian Engineering Excellence Awards, and he has visiting positions at universities such as Oxford, Illinois, Carnegie Mellon and the University of Pennsylvania. And today he's going to tell us about robots in agriculture.
Thank you very much. Thank you for the opportunity to be here. So I want to talk about agriculture and I want to talk about food and where food comes from. If we look at this graph, which shows us the population of the planet predicted on a number of different scenarios, this is kind of the root cause of a lot of pressures, challenges for society that we face today. More people means we need more resources. That's energy, minerals, metals, water. Bigger need for transportation, more people who want to go from A to B, and we need more food. United Nations predicts that by 2050 we will need as a planet to produce 70% more food than we produce now. That's a phenomenal lift in food production. We're going to need food for people, and interestingly with people, it's not just the volume, it's not the amount of food that needs to go up, it's also people's desire for types of food. And in particular, the demand for animal-based proteins is very likely to go up. And that's probably the most inefficient sort of protein we can produce on the planet. It's far more efficient to be sustained by vegetable protein than it is animal protein. We need food for animals, and this is converting vegetable protein to animal protein. Very inefficient process, as I just mentioned. So these things compete with us for food. So do motor vehicles. Increasingly, they compete with us for food. We could eat it or we could put it in the tanks of our cars. We need to put these increasing numbers of people somewhere. We need land to build houses on, and so that competes with prime land for agriculture. In my country, we've got a real demographic problem with our farmers. They're very, very old population. They're going to retire. There are some figures that say within a decade, half of our farmers will retire. That's a challenge because these people have the know-how, the knowledge, the skills to produce food. There are not young people going into food. So there will be a labour problem in agriculture, certainly in my country, and I don't think Australia is alone in this. I think across most first world Western countries, I think this is going to be what happens. If we look at the costs of inputs to farms, these numbers are all going the wrong way. So the cost of fuel, fertilisers, all of these things is going up and up. In my country, and again the data I've got is from Australia, so this is an interesting recent report, looking at farm productivity, and over many, many decades, Australia's a farm-based economy to a large extent, agriculture and minerals. Farm productivity went up year after year until around 2000, and it started to go down. This is worrying. We don't quite know all the reasons why that is. Is it a glitch? Is it climate? Is it a drought? Or is there something profound going on within the farming enterprise in our country? But certainly the fact that productivity is going down is a significant worry. The productivity of food production, of agriculture, has gone up for a very, very long period of time, about 100 years. Year after year, we've been more productive in our food production. How have we done that? There's been a few technologies that have really helped us improve the productivity of food production. One of them is herbicides. We slather this stuff over the landscape. It kills weeds, and we don't like weeds because they compete with our crop for nutrients and for water. Yeah, it makes you cringe. I can see Catherine cringing there. But this has been absolutely essential to producing food in the quantity that we produce it today. The other trend is mechanisation. So we've gone from, in the old days, human labour through animal labour, then the introduction of machines, steam, gasoline, diesel, whatever, and machines have also gotten larger. So modern day farm equipment is getting more and more massive. So this is a massive spray rig, which is very large and pumping huge amounts of herbicide onto the crop. There are problems with making machines bigger and bigger. Yeah, ground pressure goes up, they can get bogged. And if a lot of these machines, their purpose is to remove weeds. When do weeds grow? Weeds grow a lot after it rains. You want to go out there and deal with them. If your machines are very big, this is problematic. Another consequence of making machines very, very large is that the ground pressure goes up. Plants don't like ground pressure, so it does terrible things to the root structure. So where these machines drive, the ground is compressed, plants don't grow very well. And not just where they drive, but a metre or so on each side of that. So we fixed that problem by introducing what's called controlled traffic farming, which is just basically all about localizing the damage. So we use GPS-controlled machines which go up and down these pieces of crushed farmland and crush that ever more tightly and leave the rest of it alone. But still on a lot of properties, you'll find that maybe 2-3% of the land has been crushed to death and is unproductive. And if we're looking for a 50-70% increase in food production, we can't afford to crush the hell out of a few percent of the farmland. So this is a problem. So this is a state-of-the-art modern spraying machine, very large ground pressure. And think, why have we made our machines bigger and bigger? So mechanisation has allowed us to make machines bigger and bigger. Why have we been going on this trajectory towards jumbo-sized machines? And the problem is this thing. It's the driver, right? If we have a driver, then the way we make that person maximally efficient is to put him in the biggest, fastest machine we possibly can. The whole idea of a driver is kind of last century. Why do we need a driver? And particularly in a simple environment like this, we're in a farm, there's no other traffic that we might collide with. It's a relatively simple driving problem. Can we do away with the driver? If we do away with the driver, then the machine doesn't need to be quite so big. And then a lot of the evils that flow from having very big machines all go away. So this is the way Amazon managed dispatching. So in an Amazon dispatching center, we have all of these shelves in motion. They're driven by little orange robots made by Kiva Systems, which run around on the ground, pick shelves up, and carry them to the person who is fulfilling the order. So a large number of robots, small robots, all operating in parallel, are bringing product from wherever it is in the warehouse to the person who's filling the box that ultimately will be shipped to you. So can we take something from this idea of small modular robots and apply this to the agriculture scenario? So what we've built, and what I'll talk a little bit about, is a small modular farm vehicle. Speed it up 8 times. It probably should have Benny Hill music with it, going backwards and forwards. And our dream is that one day the farm is populated by a large number of these robots operating in parallel, perhaps in different fields, perhaps in the same field, performing equivalent work of one large machine. Now, a lot of virtues flow from this. If I've got 10 machines operating on my farm instead of 1, if I have 1 machine failure, in the modular case I've got 9 left. In the case of the monolithic robot solution, then I've got no robots to do my work. They're lighter, I can run them after it's rained while the ground is soft. So this is how we sort of looked at this problem of automation in agriculture and thought, well, if we take the person out, then a whole lot of constraints disappear and we can kind of reimagine what it would look like. So just to sort of a really quick value proposition thing here, a conventional machine, maybe it's 30 meters wide, goes at 20 to 30 kilometers per hour. It's got some cons listed down the bottom. If I built this little modular robot that was only 5 meters wide and it went slower, and I'll come later to reasons why it's advantageous to go slower, then I've clearly lost some performance, right? My machine is going to cover it's got a productivity about 1/24th of what that monster machine had. It's a sixth as wide and it's a quarter as fast. I'm going to need 24 of them instead of one monster machine. And trying to do some conversions into British pounds, if that big spray rig costs me 250,000 quid, then I'd need to build a modular robot for at least 10,000. So it was equal on a financial basis. So when we went into this, we thought, okay, we're going to make small robots, but they also got to be cheap, right? Otherwise, it doesn't work out. Although there are some other sort of non-dollar cost virtues listed down the bottom there. So when it comes to self-driving farm machinery, there's a huge industry around this. There's a lot of tech that you can buy. It's pretty expensive tech. It's based on real-time kinematic GPS. So it's some expensive kit, and those receivers cost many, many thousands of pounds. So I could probably spend almost all my 10,000 quid on an RTK GPS receiver and nav system. and that's not going to leave me any money for motors, tyres, or anything else. So that's probably not the way that we would want to go. If you look at what the farmer sees sitting in his tractor, looking out, he's doing the problem most in the old days, certainly before GPS, he's using his eyes, right? You can see the horizon, you can see the fence line at the end, you can see the rows of the crop. He's just going to steer his machine. So, can we do this? We know that the components of a modern vision system, the camera, the computation behind that are really, really cheap, mass-produced. You know, we're carrying around in our pockets small, quite capable vision machines, right? Phones with a lot of computation and some pretty good sensors. So this is one of the original spray rigs. That's our little prototype machine. You can see it's a lot smaller than the original machine, and that's my very grubby team of PhD students. So in order to make this thing fly, we think that there are two key technologies. One is crop row following. How do I follow a crop row, even though I'm not going to use an expensive GPS solution? And how do I detect collisions and avoid them? Now, the whole GPS thing is a bit of a mixed bag. If I've got a really expensive GPS receiver on my tractor, I know where I am to the centimetre. That's actually no use at all unless I know where the crop is to the centimetre. So in some ways, it's a very expensive solution to the wrong problem. It's much better if the vehicle could actually perceive the crop rows itself. So this is a very classical problem in robotics. I think you can find papers on crop row following, going back to the old CMU Demeter work, probably 20 years ago. It's challenging because the environment changes a lot. So we've come up with a pretty nice nav system for this. I'll set it running. Basically, we take imagery from a pretty low quality camera, we stabilize it with respect to the horizon and using inertial sensing, we warp it into an overhead view, so it's like having a virtual camera looking straight down on the crop rows. And then we have some trained classifiers that can find this crop row signature, and then we can drive to follow the crop row. So even if we don't know where it was planted to the centimetre, this vehicle can follow it to the centimetre. It follows the crop as it was planted rather than perhaps how it was designed, and that's really very important. Here's an overlay of the path of the robot on top of a view of the field. There are a couple of places where it hasn't covered very well, and that's because there's an obstacle. There was something there that it chose to drive around. So this is a really fundamental technology to really reliably follow crop rows, and we can do this in the daytime and we can do this at night. The other technology is collision avoidance, and this is interesting. If I'm a farm robot, I can't just balk at anything that's sticking up above the ground, because the crop sticks up above the ground. You might get a tuft of grass, and I can't avoid that. There's lots and lots of them. So we can't just look at the height of things. That's not enough of an indication of what's something that I should avoid. So we figured that there were really two scenarios. There's one where we want to avoid stuff that doesn't look like crop, and that's this case here. So something we've never seen before, we try not to drive on that. So we build a model as we go along of what we've been driving over, and it's been successful, so we'll continue to drive over stuff that looks like that. Doesn't look like that, we'll move away from it. But that doesn't work in the case where we've got something that looks like what we've been driving over, but it's tall. It would hurt us. So we use a mixture of the 3D structure of the scene as well as what we call novelty or surprise. And we avoid novelty and we avoid surprise. So what that looks like from the robot's perspective, everything inside that blue lasso is where it believes it's flat, and that comes from stereo vision. And everything that's in red is an obstacle that it's detected as either due to its height above the ground plane or its novelty, and it will try and avoid that. So Dave, who leads the research program, very confidently stands in front of the robot and it avoids him. And again, we've demonstrated these sorts of things day and night, and all manner of different obstacles, like tyres that are low and close to the ground. Now, the first robot that we built looks like most of the first robots that we build in a research project, kind of Heath Robinson thing, not very pretty, but it enabled us to test a lot of the ideas that we wanted to test. We hired a really talented industrial designer, and we let him loose on this problem. He did some sketches, built some little models, and then designed a very nice machine. So we have an electrically powered agricultural robot that's recently come into existence. Basically, the motor unit on each side, they are identical, and the structure in between holds implements, herbicide, whatever. That's what it looks like, and this is it in action, some of the first field trials just recently. So the central unit can be, we can change the width to adapt to particular sorts of crops. On that horizontal structure, we can put sprays if we want to do herbicide, but we can put other sorts of tools in there. We can hang robot arms down. They could be pulling weeds out. They could be picking strawberries or capsicums or something like that. So this is the current generation machine. So our approach, in summary, numerous small, cheap, light robots that can work 24/7. We can get them back in the field really quickly after rain events. We have multiple of them working together cooperatively to solve this big agricultural production problem. If we look at we've done a pretty rigorous study looking at the energy, labour and herbicide costs of say 5 robots versus a number of big spray rigs or big tractors with spot spraying or blanket spraying, and certainly the multi-robot solution seems to stack up economically. One of the advantages of a robot that's going more slowly is it can be much more targeted in the herbicide that it deploys. Much less of it will blow away. It's going more slowly and the nozzles are closer to the ground. These big things that are 30 metres wide, the booms are a long way above the ground because they bounce, and that means that a lot of it blows away. That's very bad. So I did mention earlier that one of the ways we've been able to achieve a level of agricultural production we want is by using herbicides. It has been absolutely critical to the food production capacity we have on the planet today. Really interesting thing, in my country we think that, don't do that. In economic terms, it's believed to cost something like $3 billion and go sort of to $5 billion in 5 years' time. So this is what the cost of weeds. And weeds is seems almost a trivial thing, but you add up the impact on agricultural systems, it is really enormous. There are now superweeds. So superweeds are ones that have genetically evolved to be resistant to herbicide. This is frightening the pants off the agricultural people, right? Because they do not know what to do about this. So the chemicals we have that are relatively benign in the environment, I say relatively benign, are losing their potency. So the chemicals that we can use that still have potency are really nasty and incredibly expensive. So this is a really big problem that the industry is facing. So again, perhaps an agricultural robot can look down with its camera, can look at a plant and classify it and say, what type of plant is it? Is it the crop? Okay, I'll leave it alone. Is it a weed I can kill with glyphosate? And then I will. Or is it a weed that's resistant to glyphosate and then I should hit it with something else? So I can put out the minimum amount of herbicide with the lowest potency that's required to kill that particular plant. So this is advantageous. It lets us deal with the superweed problem, but it also allows us to minimise the harm that we do to the environment. There are other ways to kill weeds besides herbicide. And there are all sorts of mechanical implements you can use to thrash them, beat them, pull them out of the ground, or whatever. There are also thermal methods of destruction on this side. I like these, so you can have either flames or this one, which is microwave destruction. So microwave, a ridiculously cheap way of doing this. I mean, we produce clystrons for about $10 in consumer microwave ovens. So 600 joules. All you need is electrons, and you can fry a weed. And this is interesting because if you don't need herbicide, your vehicle potentially doesn't need to go back and retank. It doesn't need to refuel. So you could imagine a solar-powered machine. It uses the solar energy for locomotion, for computation, for sensing, and also for weed destruction. It would just, in some ways, we've built a goat. Right, a smart goat, a targeted goat, right? They're just going to go out and do the right thing. But I think it's a nice model. You can build machines that just go and live out in an environment. When they've got enough energy, off they go, do the right thing, and then come back. Okay, last thing I want to talk about really briefly is fruit picking. We're talking about vegetables. Capsicums is the particular crop that we've targeted. In a lot of these sorts of industries, the growers find it hard to get workers. Right? Very, very hard to find people who want to do this kind of backbreaking work out in the sun. So we've been doing some work on methods of detecting using using imagery and also for harvesting capsicums. Now with a capsicum, a human would do this by grabbing the fruit and twisting it and snapping the stalk. That's ridiculously hard for a robot to do. So what we've actually done is go in there, we've got a sucker to hold it, and we have a cutter on the top. So we just clip the stalk. And it's getting up to a reasonable speed now. So it's nowhere near as fast as a human picker is. But the advantage of this is it will go day and night. So what does the future of agriculture look like? A bit of speculation here. I think modular farm robots will be part of it, of the solution. Farming is moving into being quite a complex information space, so we have a whole bunch of assets, could be people, satellite imagery, drones, and the robots themselves giving information about what's going on in the field, because every square metre is different. And so we can learn that and we can make much better decisions about how we should treat every square metre rather than we do at the moment is assume the worst and spray the hell out of it. We can do much, much better than that. So robots will be part of an information environment built around the productive land. The future might be algae. So you might have big algae growers on the tops of buildings, and we produce this green sludge and we can synthesize that into all sorts of food. Completely different future. We don't have the sorts of food we used to, we just eat algae derivatives. I really like this idea that perhaps we could have huge robots growing food on the sides of buildings. There's all this farmland on the side of buildings that's completely unexploited. And you could do a whole lot about the food mile problem, right? You want some vegetables and they're just brought down from the roof or the side of your building. That would be fun. Finally, I think what we're doing is getting back, in fact, to individual attention to plants. A long, long time ago, this is what we did, right? We respected the plant, we visited the plant, we took off the caterpillars, we removed the diseased leaves. It got individual attention. In the last 100 years, we've lost all that. We treat, as I said before, we expect the worst, and we spray a huge amount of chemical on there to deal with the problem. So perhaps we then move to robots which are providing individual attention to a plant. So in fact, a robot peasant, if you like, a goat, peasant, whatever metaphor you prefer. So that's a really quick introduction to perhaps the potential for robots in agriculture. Think about where the food you eat comes from. There can be real problems with producing enough of it for everyone on the planet, and they are some of our sponsors. Thank you.
Thanks, Peter. I love the idea of a robot peasant goat. On that note, are there any questions from the floor for Peter? One at the back.
Hi. How are you going to prevent theft or vandalism if these are unmanned?
On farms?
On farms, yeah.
I don't know. We already have we have theft of animals at the moment. So cattle duffing, sheep duffing, it happens. I guess the machines could report if they're being interfered with. Network back to the farmer, he can go out with his gun and confront the person. It will be an issue. I think with all sorts of autonomous systems that we put out into the environment, theft is going to be an issue. You know, whether it's a museum guide robot, an autonomous pod transporting people around, they are going to be stolen, they're going to be broken down for parts. There's going to be a whole black economy built up around this.
So we need an armed peasant robot goat. I think the lady here had her hand up first.
I see in terms of your supporters a lot of government support. How about big ag companies like Monsanto and Syngenta? Do you have any sense of the type of investment that they're putting into this field?
Into automation, I don't know. I suspect not very much. If you look at the big traditional manufacturers of farm equipment, they are mostly aware of it. They have very small internal teams working on this. But I think the management of these companies is not convinced that automation is the way to go. I think they are like many industries, photography, music, whatever. They're going to wake up one morning and wonder what happened. I think at the moment they just don't get it. So there is a lot of work happening. There's a bunch of companies in California where it's kind of the epicenter of so much robotic action. There are a number of small startups now looking at robotic agriculture, but they're most of the research that I know about around the world is still government funded. A huge number of EU projects, for instance, and there are projects in this country as well, in this space.
I'm just related to that, one of the online questions was how do you reach small farmers to get them to adopt the RAS technology? And presumably cost is one issue, but is there a demand from them, or do they like to drive their tractors?
I think if you could free them up from having to drive the tractors, I think it would be a big attraction to them. I'm not sure whether they need to own the equipment or whether they could rent the equipment. Maybe everyone owns a few and then they share them around to deal with peak load.
Yeah.
For agriculture, there's a lot of timeliness in what they do. But when the crop's ready, you can't change when it'll be ready. Then you need to deal with it as quickly as you possibly can.
Yeah. So it's capacity.
For spraying weed spraying, it's not so time critical, but certainly for harvesting, it's all about timing.
Yeah, right. I think there were two more questions around the middle.
Yeah, this was actually a question I thought of this morning in David Lane's presentation on marine robotics, but it actually connects to this because it just occurred to me. We've got fish farming, etc., sort of in the marine. So I just wondered, I'm no expert or know almost nothing about robotics, but is anyone looking into the idea of using robots in the marine environment to even produce a new agricultural type of industry to expand the rather limited use that we make of the oceans in some ways, to maybe use it in a more effective, better way?
I believe there has been a little bit of work on robotics and just monitoring technologies, just to count how many fish you've got, what's the size distribution of the fish that you've got in your pen. I don't know more than that. David?
It goes to the extent that I'm aware of.
Big voice.
Peter's right, there's not a lot of sort of robot in the fish farm. There are some ideas knocking around about how can robots better support fishermen, right? And that's everything from dealing with where the fish are, to helping control the nets, to understanding which way, trying to count how many fish there are, and which way are they oriented relative to the sonar on the ship, so you can count them. So there are some sort of the same thing really, sort of supportive, sensing type applications, but they haven't hit mainstream yet. And our attempts to get them funded from European Horizon 2020 projects have so far failed. So.
Another question in the middle, at the back.
Great talk, thank you. Slightly more general question. I'm just curious. Us here in the West, we're very lucky to have lots of resources and large fields and big tractors and all the rest. But a large part of the world's population, there's a lot of very, small farmers or for people, doing agriculture. I don't know. Does robotics have a place in that? Maybe it doesn't make sense, but maybe it does. Are there any efforts in that kind of space? People doing, agricultural robots to kind of help the poor farmers of the world, but maybe that doesn't even make sense. Just curious.
It's a really good question, and I don't have an answer to that. I know that this trend towards urbanization, which happened in the West, happened hundreds of years ago, I guess, with the Industrial Revolution. People left the farms and piled into the cities, for better prospects, better life. And I suspect the same thing will happen in China, and the same thing will happen in India. And we heard the figure this morning of 40,000 new cities being built. And humanity moving into an era where for the first time more people live in big urban concentrations than on the land. So I think there's almost a sort of inexorable exit of people from farms into cities. We started a lot sooner, but I think other countries are going to follow similar trajectories. So I think you'll probably have a labour deficit on the farm. So we've got more food needs to be produced. People are vacating farms. Who's going to do the work? Added to this is the whole problem of the ageing demographic. So in my country, the demographic, the farmers, they're very, very old. They're going to retire. All around the world, we're going to an increasing number of more elderly people. So there's going to be there's less people of working age to do the work of supporting all of the population. If they're leaving farms and going into cities, then we're going to have a really big problem. So I think any sort of technology that can assist on farms is going to be useful. I mean, some countries it's just going to be mechanization. You know, it's going to getting rid of the ox and having a tractor. You know, that's going to be the first step. Maybe it's not automation, but it'll definitely be mechanization.
I was wondering about water, because it sounds like that's actually going to be the limiting resource in the future. Does robotics make any contribution to that? Or ameliorating it, not making it worse, hopefully?
I don't know how robotics would influence the water problem. It could be that we move to very sort of water efficient farming, but that would be indoors. Yeah, perhaps variants of hydroponic farming or whatever. So big greenhouses, very optimal use of water, and perhaps you have machines that are tending the plants within those, if you like, artificial environments. That might be one answer to the water problem. You could use robots to carry water to plants, but I think it's probably cheaper and easier just to use pipes and drip systems. Yeah. Yeah. Yeah.
So a couple of quick questions to finish before coffee. You talked a lot about the battle against weeds. Mm-hmm. Is there a more intelligent way that we could harvest them and use them efficiently and robotically rather than trying to zap them?
It's a good question. I don't know the answer to that. Maybe we harvest them if they're edible. Yeah.
Or energy. And the other question was, can the robot identify hidden obstacles as well? Possibly the chap lying in the grass.
Well, he's not that hidden. It depends what you mean by hidden.
Or maybe small things that might damage your equipment, I guess.
If the sensing modality you want to use is vision, then no, vision is no good for seeing things that you can't see. So then maybe you use radar or some other kind of sensing modality to see through that. So yeah, one of the things we're worried about, if there's a great big rock, behind some grass, what are we going to do about that? At the moment we figured that's not a big risk because this is land that's been farmed already in traditional methods. So any obstacle or rock that was there, it's been taken away. Maybe a tree will fall down, but then the sensing techniques we have would detect that.
Yeah. Okay, that's fantastic. Thank you very much. We will break for coffee. And if we could return here for 20 to 3, please, and thank both of our speakers for excellent talks.